they told me that I have to entertain you for 10 minutes, but I'm not so good in entertainment. So I will just have the pleasure to introduce Carla, which is from Cornell University. She is the founder of the Institute for Computational Sustainability. Carla is a computer scientist of Portuguese origin.
Yes.
I don't think I will spend more of the 10 minutes. Carla, you have the floor.
Thanks so much, Alex. Yes. Thank you for this amazing workshop and for having me here. My talk is a little, maybe a slightly different picture, but I will talk at some point a little mechanism design a bit, but I thought I would tell you, about computational sustainability and about AI and how I'm really focusing on advancing scientific discovery. And yeah, I guess this doesn't work. Oh, it does. So let me, in case you wonder what computational sustainability is, this is a new interdisciplinary field that really the idea is to use computational methods to address sustainability in terms of the vision for sustainability is really sustainable development. And Marta yesterday gave a very nice chronology of sustainability. A key point is indeed back in '87, the Branson report that introduced the notion of sustainable development that meets the needs of the present without compromising future generations. But future generations, they stress, because often people think of sustainability just environment. They stress that now, sustainable really encompasses balancing environmental, economic, and societal needs. And as you are familiar, more recently, the United Nations put forward the Sustainable Development Goals. So there are the 15 goals. Of course, in general, people have no clue about this. This audience knows all about the Sustainable Development Goals, so that's good. But I see, Sustainable Development really, the ultimate goal is human well-being, and that's the big picture. Of course, if we are trying to tackle these problems, this is highly interdisciplinary, which makes, very challenging for us. I always like thanking NSF, frankly, NSF really has supported this research, back in 2007 we had a large expedition in computing award that really allowed us to establish this field. We had a second expedition with a large network that Computational net involving several universities that really allowed us to push this field significantly. We are also pushing, this AI for science, and we actually started a center recently. And again, intersection of AI, sustainability, science, material science, physics, and biology. This is funded by a program for postdocs by the Schmidt Futures. And more recently, we are starting an AI for Climate Institute that is very recent. And there, actually, I will see many questions concerning mechanism design, because the goal is really to accelerate adaptation to climate change and mitigation, and really address the carbon markets. So there will be really opportunities for mechanism design. Of course, I always like thanking my students, because in the end, they are you guys are here, they are the ones the bees who actually do the work. So thank to all my students. So today I thought I would give you a perspective in terms of AI to accelerate scientific discovery and improve decision making. Several people mentioned decision making, and I will give you a sample of project examples. For example, AI to combat the decline of biodiversity. I will talk about AI to reduce adverse impacts on people and nature of the Amazon hydropower expansion. There have been a huge proliferation of dams in the Amazon, and I'll talk about that. And maybe I will talk a little bit about AI to accelerate materials discovery for renewable energy. So, what is exciting about all these projects, as computer science, they all may seem completely separate, etc. But one thing I will emphasize throughout this talk is, the synergies, and I find it very rewarding. By working on birds, I actually developed very exciting models that are allowing me to predict better properties for materials. So all these synergies is really, a key aspect of computer science. As you know, the notion of reduction, we actually see them in practice. So I like that. So, from a computational point of view, I will talk about, bird conservation and, in particular, multi-level learning and challenge in citizen science. I will talk about AI for balancing environment, economic, and socioeconomic needs. The main topic is going to be, how do we design more ethical decision support systems, and I will talk about multi-criteria optimization and computing operator frontier. And I will talk then about AI for accelerating discovery of materials, and here is basically about the challenge of doing discovery with very no label data. So how can we do this unsupervised learning when we really don't have a lot of label data? We have a ton of data, but not label data. So I'll start with bird conservation. As you know, we have witnessed an incredible decline in species, and one question that's central in terms of biodiversity research is to understand how species are distributed across landscapes over time. And to do this, typically, we combine all kinds of data from a variety of sensors, but also, Landsat, satellites, remote sensing, etc. But also a very sophisticated, I realize it's cutting a bit of my talk, but that's okay. A very sophisticated sensor, that's the human sensor. So, the Cornell has this lab, the lab of ornithology. We have this program, eBird. eBird is a citizen science program. Anybody can submit bird observations from age 8 to 98 or more. And so we have, lots of volunteers, almost 1 million, who have submitted a ton of observations. And in fact, the time would be building the Empire State Building more than 4 times. And by combining the data from the eBird with the environmental data, we can really develop these adaptive spatial and temporal models to uncover the bird migrations and the patterns of occurrence and absence of the species. And in fact, we use this data to inform, for example, the State of the Birds report is based on this data. What you see here is actually the output of a machine learning model. This model is a single species model, so what we've been doing now is, to improve the accuracy and the performance of the models, and also to really understand the interactions of species, we are developing joint species distribution models. But these models are very important because they allow us, and here you have an example of mechanism design, where basically you want to conserve land, you want to protect the species. This is an example of how we are using this in combination with the Nature Conservancy to provide habitat for birds. So, there has been a tremendous drought in California, depending on the years. So, in order to provide habitat for the species, basically, you see this is the Pacific migration flyway that we can predict quite accurately. And so based on that, we can, the Nature Conservancy allows, has this bidding process with combinatorial reverse auctions. And the idea is rather, buying land could be very expensive and you could not buy the entire land, for the birds. But what you can do is, coinciding with the bird migration, the farmers can submit bids to keep the water in the rice fields, and that provides habitat for the birds. And so, that is a very nice and relatively inexpensive way of creating habitat, and this has really generated substantial habitat for the birds. And this is only possible because of this, very dynamic models that can, predict and combine with combinatorial reverse auction. So this is a good example of, mechanism designed for conservation. As I mentioned before, the standard models used by ecologists, and in fact a lot of the models are really single species models, but it's really, ecologists know that it's very important to understand the interactions of species with the environment, but also with each other. And so part of our work has been really to develop these joint species distribution models. But it is actually very challenging from a computational point of view. And the reason is because, if we want to develop the joint species distribution models, we have to, estimate the covariance matrix, and standard models don't do that. Just at very high level, we actually, what we've done is we have incorporated this multivariate probit model, which is a Gaussian model with deep learning. And so we have basically an encoder that produces this structure latent space, and that will be really computing the mean for this multivariate Gaussian and the covariance matrix. As I said, this is actually challenged. Like, I don't know if you are familiar, for example, VAEs, variation autoencoders, assume the matrix is just a diagonal matrix, so it's, assume, basically they assume independence. But it is key to actually compute the interactions, and here I show it at a very high level. And I'm showing this because I will show that other very different problems can leverage from the same idea, where we have a latent space that's, in this case, keeping track of the mu for the birds and the covariance, and then we can compute the joint species distributions. So with this, now we can actually predict jointly the species. What you see here now is an animation with the migration patterns of 41 species, jointly. In fact, this 40, there's one missing here, the Wagner distribution. So, And this actually, what was important for us is by working on this, we actually realized that it was super important to understand the interactions of species, and that's why we actually developed this idea of an interpretable latent space. And I'll show how that plays a key role in other models. So here we show, the projections of the latent space, the habitat interactions, the birds and the species interactions. And, this allows the ecologists to actually validate our models very, carefully. And, again, this model is developed initially for joint species distributions, but it's a very general model. In fact, we use this model also for other applications, including, multi-object detection for computer vision and material science, etc. In fact, we extended this. Is Jude here? We had a collaboration, and he was part of this collaboration with the Gulf of Maine. We extended this model for fish, for predicting the biomass of fish, but more interesting in the sense that quite different. We actually extended this model, a variation of this model, to predict the density of states for materials discovery, and again, it's a very different domain, but essentially, you can think of a regression problem where you want to estimate, in this case, the density of states or the species of abundance for fish. So, well, all this relies on citizen science. And citizen science, that's a very nice way of acquiring a lot of data, but there's a fundamental problem. Obviously, we cannot really tell the citizens where to go. They are not paid, and therefore, they really collect the data based on their preference, on convenience, etc. And in fact, if you look at here, we see almost where the cities are, because that's the bias that you get from this data. So one issue is, how can we try? We try to correct for this the bias via the algorithms themselves, but we actually are also developing these games. And again, this is another good example of mechanism design to incentivize people to go and collect distributions in a more uniform way. And in fact, so we use this principal agent framework where eBird, that's the principle, is going to replace, basically the game replace points so people can collect the points, and at the end of the season, they get prizes proportional to the number of points they collect. And so what's the game? We have to design the game as this bi-level optimization problem, where we place the points knowing that the citizens, the eBird, see the points, and they are going to maximize their own utilities and move accordingly to their interests and the points they collect. And we want to do this in a way that is going to induce a more uniform distribution. So this is a bi-level optimization problem, and that includes two problems. The pricing problem, where to place the points. Here we just place the points and we don't, they get prizes. Interestingly, we ran the same game in Africa, there to collect data for vegetation, and there we actually pay the herders money, little money for us, a lot for them. Here we just give prices. And so there's the pricing problem, and then there's the identification problem, where we need to identify the preference of the users so that we can, run the game accordingly. So, and actually, Yeshan was super involved in this game. In fact, there is Yeshan there. So, we were quite surprised, when we launched this. And, the nice thing about working with, like the lava-flow ornithology, it's a very long word, so we should say lava-flow, is that, when we come up with these ideas, they say, oh, this is amazing. And literally, like in a month, they implemented the game for us. So that was very exciting. And now they actually have ivy caching for the desert, for example, in California, where they want to understand the impact of solar plants. What do you call?
Panels.
Panels, but the farms, solar farms, correct? And so they ran this game. And you see here, we were able to get people to go to other places to make, less concentrated. So that was quite exciting and positive. So, let me now talk about another very different problem. And here, this is, I think it connects with this group nicely. It is this idea that indeed when you are, designing, when you have decision support systems, you cannot just optimize with respect to a single goal. And basically, we've been working, studying strategic planning for the placement of hydropower dams in the Amazon, not just Brazil. This is a dam in Brazil. And so, from a computational perspective, this is really how to really do multi-objective decision-making or design more ethical AI systems that consider a variety of criteria instead of, a single objective, energy. So, basically, about 200 dams have already been built, and they are planning over 300 new dams for the Amazon area. And so a key question is, how to select the dams to build. And so this is really, the way I like phrasing this is this idea that we need to develop more ethical systems that are going to look at trade-offs and understand, the trade-offs with respect to different objectives. Because if you think of a river, a river or hydropower dams do provide energy, but, fish, the populations really rely on freshwater fish, sediments and nutrients. The connectivity is key for transportation, navigation, fish migration, and there's also this the river, if it gets disturbed, how it regulates itself. But of course, there's also deforestation, displacement of populations, flooded farmland, and we always think of hydropower dams as clean energy, correct? That's what we think we are getting. Well, it turns out that quite often dams can flood huge areas, which leads to the decomposition of organic matter and release of methane. So dams can actually be dirtier than coal. So that's not nice. So we've been looking at how to do strategic planning in terms of dams and really by studying the Pareto frontier. I guess you are familiar with the Pareto frontier. Here I show an example where with two criteria. This is hydropower energy versus an ecological value. If I don't build any dams, obviously I don't get any energy, but I keep all the ecological value. If I build all the dams, I have a lot of energy, but I destroyed completely the ecological value. So here you have the situation in between, and this case is dominating this one because for the same energy I can get much better ecological value. So this configuration of them dominates this. And for you to see in terms of, for example, if I'm going to look at the criteria connectivity, you know, this has a much better connectivity because I'm placing, you know, the dams away from the mouth of the river. So I will not get into the technical details, but you know, obviously computing the Pareto frontier is a very challenging computational problem. So interestingly here, you know, and frankly I never thought this would happen to me in real life, you know, when we talk about fully polynomial time approximation schemes, so that's a fancy algorithmic language, but actually here we have that beautiful situation. Because given that the river is a tree, you know, as you know in computer science, often when we have trees, we can exploit the tree structure and use some divide and conquer algorithms to actually have approximation with guarantees. So we develop an efficiently approximate algorithm for this, NFPTAS, fully polynomial time approximation. So this is basically based on dynamic programming, and you know the main challenge for these algorithms, and the more criteria you have, the you know the more challenge it is, because computing the Pareto frontier is really exponential in the number of criteria. And so the key challenge is to remove these dominated solutions. How can we do that fast? And so we develop an algorithm that actually gets very general, that can remove dominated solutions in or the n log n by using some kind of general divide and conquer algorithm, and have other strategies. In fact, and I'm going to tell you, if you guys are using only Python, yeah, that's not going to cut it. I'm sorry to give you the bad news. And in fact, this is a good example where, you know, I had actually a postdoc who was working on this and basically implemented this algorithm in Python. And so, you know, the Amazon basin is huge, and there's this, I used to call the little Marathon. There are many languages here, but which is, you know, a sub-basin, it's the river. But, you know, I actually have been to the Marathon, and it is majestic, it's not baby Marathon. But in the big picture of the Amazon, the Marathon is just a sub-basin here. It's just a little sub-basin and very small compared to the big city. However, just for that sub-basin, a Python algorithm with 2 criteria, after 5 days it was still running. And in C++, we could compute without the fancy algorithm to remove solutions, with C++, we could compute it in 1 minute. I mean, crazy. I mean, it is really insane. And obviously, you know, for the entire Amazon, we can actually compute the exact Pareto frontier for 2 criteria in a question of, again, a few minutes. Of course, when we add more criteria, eventually this really, we can, so this algorithm allows us to compute the Pareto frontier with the guarantee. So it's a trade-off. I can say, well, I want the exact Pareto frontier, which for the entire Amazon for more than 2 criteria, we can't really do it in reasonable time. Or I can say I'm willing to get the Pareto frontier with an epsilon of 0.01, or, you can give the guarantee 1%, 2%, 10%. For example, for 6 criteria, we can only give a very, very loose guarantee. But so that's the trade-off. So here I show basically the example to show that what you see here is, and visualizing it's another challenge. When you have several criteria, 2 criteria, it's obviously easy to visualize. More than 2, it becomes very difficult, and I'll talk a little bit about that. So here you see the Pareto frontier for energy and river connectivity, and here we plot the Pareto frontier, assuming that we plot the Pareto frontier before any dam had been built, correct? So here we have the optimal Pareto frontier. What I show here is the situation today. The existing dams are right there with this amount of energy and this amount of connectivity. So what we can emphasize here is this is the foregone environmental benefits, correct? For this amount of energy, I could have had much, much better connectivity if I had picked better dams. So I lost these environment benefits, or these are the foregone power earnings. I could have had much higher level of energy of destroying, fragmenting the river for the same amount. And here is the Pareto frontier now going forward. So you see this area was all gone. Of course, we have we are looking at a multitude of criteria and connectivity, sediment, people, etc. And here I mentioned at the beginning the Pareto frontier is a little odd here because here we are actually minimizing carbon emissions. So if we had, we could have plotted the negative of this. That's why the shape of the Pareto frontier is different, because here we want to, for a given install capacity, minimize the carbon, greenhouse gas emissions. And this is a case where you see all these solutions are dirtier than coal. And it is, a little paradoxical because, it was counterintuitive, the fact that, you can have really bad solutions that are dirtier than coal, even though in general you think of hydropower dams as clean energy. And in fact, here we look at the projections for the 2030 agenda and compare, how we would be placed. And the big message is we are getting really off that track. But the main message here is you need to choose dams properly, otherwise you can have solutions that are dirtier than coal. Here, basically, and somebody yesterday we were talking about, or like Meline was asking, how we decide. Indeed, in the end, decision makers have to make decisions, but at least we tell them the scenarios, correct? And this allows us, for example, to identify dams that are really bad in all the solutions. So, those are the ones we are not going to, in fact, we have this paper in Science and we are not, advocating for any particular solution. But this is like a framework that really allows them to understand, the impacts with respect to the different dams and make solutions. You see here that we compare the Pareto frontiers for different criteria, and you see that connectivity, there's a huge gap what we could have obtained versus where we are. Another one, fish biodiversity is really being affected dramatically. So this is important for them to understand the trade-offs. And in fact, you know, we actually developed these tool, Amazon ecosystems, where you see, literally, because we are computing several criteria, it does make really sense to just look at 2 dimensions. Those are easier for us to see, but you need to think about, you know, the 6 criteria. And just for you to see, and I'm pointing to this group, and particularly you are Nicholas, the number of solutions we obtain here are in the order of billions, you know, because the more criteria you add, then you can differentiate solutions, correct? So it grows really exponentially, it's crazy. But then, you know, this tool allows us to, for example, and I'll show here. Here we say, okay, we want just solutions with 80 gigawatts. So now we are constraining. We can, in fact, I have a student working on, you know, generating the Pareto frontier with bombs. So that allows us to actually eliminate more solutions. And here we are constraining the energy to just 80 watts, and then that allows us to reduce, you know, the number of solutions dramatically. And you can play with this thing, you know, with the bombs and to look at different solutions. Or then you can look at the separate Pareto frontiers. But to be honest, you know, communicating this Pareto frontier is in itself a big challenge, because, you know, there are so many solutions, and we are not really suggesting a single one, but we believe that by giving these tools that's helpful. So this goes to when?
Well, leave a little
Yeah.
for discussion.
Yeah. So my final topic is, so I thought I would sample some projects to cover different topics. And, you know, this is concerns, you know, using, you know, AI and for accelerating discovery, scientific discovery. And in fact, I mean, I have to say, ChatGPT is taking over rapidly. You know, make my own research. You know, I have actually always, I mean, I'm very much interested in obviously sustainability, etc. But I'm really passionate about, you know, AI algorithms, and so because of that, you know, somebody who was Zoe, I'm always picking on Zoe, not good. But you were talking about, you know, going where the data, where we have the data, which is obvious an issue. But I admit and confess that I also tend to go towards problems that, you know, the state of the art is not going to work, where we do need to push the frontiers of AI, and because that's my area, and so I want to contribute that way. And I think, you know, science is really the next frontier for AI. You know, ChatGPT is very good, but coming up with discovery, I think, for a while, but not long, it's still, you know, a huge challenge. And I'll talk a little bit about that. So basically, I'm going to talk about, you know, scientific discovery in a context where we really don't have labeled data, you know, to train on. And in particular, just I'll give you a very, you know, back in 2010, you know, the Obama administration launched this program, the Materials Genome Initiative, really to accelerate the pace of discovery of new materials and reduce the cost. And, you know, this is really exciting for AI because, you know, it's really, it is based on, you know, using massive computation to, you know, interpret data and do discovery. I have been working with, you know, several groups at Cornell and also Caltech, and focusing on solar fuels. And contrarily to, solar panels, solar fuels can actually be stored and used later. So we are not dependent on, the intermittence of the sun. I can, generate the solar fuels, store them, and use them at night. Just a very, at a high level, how do they do this material discovery? They use these techniques, co-spectrum techniques. You can think of, let's say you have a silicon wafer and then you do atomic spray painting of, let's say, 3 metals, gold, silver, and bronze. And so you get this mixed thin film, and then typically you do annealing, etc. And with that you can generate lots of materials that result from the combination of these 3 elements and synthesis. So to understand the materials, it's important, to characterize them, and often they use X-ray diffraction pattern, X-ray diffraction, like high energy. This is the synchrotron actually at Cornell, using high energy to characterize the materials. This is very similar. You are familiar with obviously DNA. That's what Watson and Crick did, using X-rays to identify the structure of DNA. So, but here is applied to materials, and this is really inferring the crystal structure of the materials based on X-ray is very challenging, particularly because actually the structures can get mixed up. And so while this can be done, we can synthesize lots of materials a day and characterize lots of materials a day. This task of inferring the structure of materials from X-rays is really tedious, and they can do a few systems a year. So that's what we are trying to automate. More formally, basically, this problem is, now I put here a ternary representation. Here you have ferro, you have iron, aluminum, and silicon, 3 materials, and you see they got mixed up. For example, here you would have 50% of iron and 50% of aluminum. Here you see, so you get the mix, and these are samples that we can collect, and what you have here is the X-ray diffraction pattern. So we take the samples to the synchrotron and get the X-ray diffraction pattern. So the problem we are trying to solve is identify the different regions that are formed, because each region corresponds to a different material. And so, basically we want to output the different M regions, K pure regions, like this is a pure, this is a pure, this is a mix, and we want to also give you the X-ray, the pattern that characterizes that region. So you could think of this as clustering, except it has to be a clustering that has to satisfy thermodynamic rules, which I'm not going to go in detail, but basically, the phases are connected, and then there are some rules that says, well, if I have a mixture of 3 elements, then I can have at most, explain that with at most 3 phases of crystal structure. So there are all these rules that have to be satisfied, and a clustering algorithm is not going to give you that. Another way here is, for example, I give you this point, and this is a pure phase, and I exhibit, the pattern. This point is a mix, so I want to actually show you the 2 patterns that correspond to 2 crystal structures that explain that point. So that's what I want to do. So this problem is relatively easy, but but when we develop methodology, number one, I always tell my students we have to develop general algorithms. It can't be just for a single thing, so we'd better go and find other problems that are similar and can, do this. And, and in fact, when you write this for a computer science audience, they immediately say, this does not belong here, go somewhere else, correct? So, I made up this little problem that is, basically multi-MNIST. Everybody knows multi-MNIST, the MNIST, correct? Sudoku, where here, if you look at this is basically two Sudoku. I assume everybody has played knows Sudoku, correct? So these are two Sudokus, and the task is I give you this, and you want to demix these two, demix the digits, so you have two Sudokus satisfying the Sudoku rules. It's like you demix crystal structures satisfying thermodynamic rules. Here you demix characters satisfying Sudoku rules. And, interestingly, this is, again, a particular case of a more general problem that, for example, we do a lot of, for the birds, flight call detection and bird vocalization, and again, you are given an audio recording, you want to separate the sounds, separating the bird sounds from the rest. It is another, source separation problem. So all these problems are computationally very similar, and we are actually working on all of them. And actually, also music separation. I listen to a piece and I want to know what instruments are playing there. So all these problems are very similar, computationally speaking. Of course, why is this so challenging? Because in our case, we do not have label data. We have zero label data. We have data, and not even a lot of data. And so, the current state of the art really is failed to capture the underlying physics, and therefore, the way we do this, we combine, machine learning with symbolic AI to do this. So, just for you to have a sense, if you look at this, can you tell me what's there? Can you actually guess? You see, numbers, letters, but you don't know exactly what it is, correct? It's hard. Now, if I tell you, well, this comes from two Sudokus, where you cannot repeat the symbol in a row and in a column, maybe now you can start reasoning about it. And that's exactly what we did. We are using this problem with unlabeled data, and we can actually separate these two Sudokus by, combining deep learning with reason about prior knowledge, where here prior knowledge basically is the Sudoku rules, correct? And, do you have a question?
Yeah, if you don't mind.
Oh, no, my God.
Prior knowledge, you also have some prior knowledge of what the digit is and what the letter is.
That is very good. I have prior knowledge about what a perfect digit is, but I actually don't have training data on the overlapping Sudokus. But I do assume that we know maybe what the digits are. That is a very good point. And so, basically again, and ironically, this structure was inspired by the birds, where we have an encoder that produces a latent space, and this latent space actually is going to keep track of the probability of the digit, the possible digits and the shape of the digits. And then we have a generative decoder that is going to reconstruct the image. And, again, this is very similar to the bird, the one that we developed to predict the giant species distributions. Just as a detail, you may say, and in fact, we had, this paper was actually published in Nature, and one key question was, why isn't this just optimization, correct? You could think, because we don't have any label data, and we actually show that even though we don't need a ton of data, we need about 100 Sudoku instances because you learn the structure across the instances. So that allows you to actually, in addition to the rules that you encode, you get to learn across the instance the structure of the instance, which is very key. But of course, I just showed you the Sudoku problem as a toy problem because it's easier to understand. The real problem is actually this problem, where we are given 300 unlabeled X-ray diffraction patterns, and to David's question, we know the theoretical crystal structures that have been observed in, so this is the bismuth copper vanadium oxide system. So we know theoretical crystal structures observed there, but these are without any noise. And our goal is to see if they characterize this. So we mix this to get this. And indeed, here we were able to demix the crystal structures, and we get the crystal structures here. And in fact, they form all these regions. And contrarily to, for example, in the Sudoku, we knew a priori there were 2 overlapping Sudokus. Here, we don't know a priori if a region is going to be explained by 1, 2, or 3. And you see, for example, A is explained by 3 phases, B by 2, etc. So, and actually, this particular region, our collaborators were able to discover a new material for solar fuels. And as I said, in contrast to the standard solar panel energy, solar fuels can be stored for later use, which is very convenient. Again, you see, the same very similar structure where we have an encoder, produces an interpretable structure latent space. We can then use thermodynamic rules to reason about it, and the decoder in this case is a Gaussian mixed model. And again, you see, very similar to the structure of the Sudoku and the structure of these DIMACS for the demixing is similar. The key is this interpretable latent space that allows us to reason about it. We are, pushing this. We actually have another big MURI, which is, funded by AFL-SAR. And the idea is to develop SAR, a scientific autonomous research agent for materials discovery. And what you see here is a depiction of SAR controlling, this has a mixture of materials, and you see this laser is actually doing the annealing. And SAR is really deciding where to go and for how long it can control temperature and dwell time to produce the synthesis, and then we have optical and X-ray characterization of the materials. And here is the phase diagram for this. So, obviously, all these projects, and that's a key rule for me. I only work on projects if I have, access to the highest level of expertise in the corresponding domain. And here is, my colleagues, the material scientists, and actually this paper was led by computer science together with the material sciences. So this is a student, and this is a postdoc. Okay, so again, I always make sure that we publish our work in CS, in computer science, but then, this work has to be validated and go in the, corresponding domain journal, so that we are not just, making up stuff. And it makes it quite challenging. There's a huge learning curve for the students, but, it's also rewarding. So let me wrap up. And, I gave you a few examples, but, we have many projects. And here you have this subway line, and basically what I highlight is the lines here correspond to topics, computational topics. And for example, I talked about this pattern demixing for the Sudoku and for the the crystal structure phase mapping. You see this blue line, but obviously we are working on stochastic large-scale spatial and temporal modeling and prediction, for example, for species distribution. We are working on large-scale spatial decision-making, etc. So many other projects. But we emphasize the cross-cutting computational things, and that's what. And in fact, Sarah is not here, but I think to some extent we try to work on these projects, but then different students can leverage their expertise to emphasize in different domains. So I mentioned too that I already emphasized it's also exciting because ideas that for example, we developed this model for I'm sorry. My back to you guys. I just realized that a little late. So, for example, really models that we developed for birds became key for materials discovery, and these synergies are really exciting and really give us new ways of thinking, and by transferring knowledge across domains, which, by the way, ChatGPT is going to be very good at, is really empowering. I talked a lot about this line, demixing Sudokus or demixing crystal structures, but I also talked about large spatial temporal and structure modeling and prediction for birds and materials, etc. We've been talking a lot about AI, and over the recent, everybody talks about data-driven AI, machine learning, etc. And of course, that's true given the huge progress in terms of image identification, face and speech recognition and ChatGPT. But challenge when it comes to scientific discovery and decision making, I think we still have a long way to go. There are many challenges that we need to address. Typically we want to, understand and explain phenomena beyond just prediction. We want to understand causation beyond correlation. Typically we have very small and labeled data sets, and a lot of the tasks, actually the majority of the tasks, are unsupervised. And then when it comes to decision making, we need to make choices, and often, combinatorial choices, and really, with respect to many criteria, we should really understand these, Pareto frontiers. And, high dimensionality of the problems, which I think actually AI can really play a big role in helping us think in high dimensions. So, pure data-driven AI is not really suitable for scientific discovery and decision making. So I'm in favor of combining data and knowledge to really be able to reason from first principles, reason about uncertainty, and dealing with combinatorial decisions. And I also think with going, high dimension and understanding Pareto frontiers is important to develop more ethical AI systems. In summary, this has been quite an exciting journey for me. I focus a lot on this in terms of advancing computational sustainability. I see this really a two-way street that on one hand, we are injecting computational thinking insights and methodologies to tackle these very challenging problems, but on the other hand, we also get new challenge problems, and often actually by talking to the scientists, you come up, they actually have very good ideas, poorly computationally speaking in general, but that's where we come in, and we can identify new paradigmatic problems in computer science and hopefully have some societal impact. Thank you.
Okay, thanks. You have already a question.
I've been waiting.
Okay, thanks Carla for this exciting talk. we have some time for questions. So, Fredrik, who is...
I was first.
Yeah.
So please.
Thank you.
So when I first saw your diagram with showing what Pareto materials, my first thought was to go back to yesterday's discussion about index numbers.
Yeah,
And I said, how on earth do you measure ecological value when there are so many different components to it? So then, of course, I understood that you were doing the same diagram for each of the different components of ecological value. But even then, I would have some questions. So, biodiversity being one of those things, there is no one single index for biodiversity. It consists of so many different components. So how do you do that? How do you actually produce the y-axis?
That's a very good question. And like for example, for the Amazon, we are looking at the Amazon basin, and actually now we are looking at another basin in Colombia, the Magdalena Basin. That, for example, there we could potentially consider about 300 species of fish. And so we could potentially look at the Pareto frontier for all of them. And of course, that becomes overwhelming. So we are going to maybe just look at main species or genera or something. But in the end, for example, we did collapse, even I showed here a Pareto frontier for fish biodiversity. We ended up collapsing the fish biodiversity to an index because, to have some way of coping with it. If we go species by species, it becomes overwhelming. So, it's a good question. We don't do a single index, but we still have to somehow, convert, and in the end, for us to perform these optimizations, obviously we have converted things into numbers, correct? So, But these are very, very good questions, and it's very dependent. That's why even for species, we think it's important to consider the different species, because different, local indigenous population appreciate different fish, and therefore we want to, highlight the impacts for this particular species because it's going to affect this particular group of people depending on them. So you see, you can go back and forth, aggregate, and then provide a finer characterization. So. Yeah, there's not a good answer or a single answer for that.
The related question, so you have different, some of them it's easy, I assume. So connectivity, you have 0 to 100, and that's a percentage.
No, connectivity is very, actually that was the first criterion that we used because we didn't depend on anybody to give us the data. From satellite, we can get the river network and literally, measure each little leg. By the way, this, and it's quite remarkable. We are talking about about 5 million river segments. Yeah. So, and we can actually compute all of this. So, I didn't explain exactly how we do, but we basically have a graph. It would take me, interestingly, the nodes correspond to building dams, and then, the nodes correspond to the areas that will be affected by the dam if you build that. So, but the connectivity was the first one we actually used because it was very easy to get the data for that. We just needed satellite data, and then we could get all the data for the lengths of the segments.
So, and I don't want to dominate this, maybe other people, but one more question, as long as I have the floor. Depopulation.
Yeah.
How do you measure that?
Very good question. And in fact, for example, I admit for our science paper, we didn't even include that because, we couldn't even vet the data very carefully. And it's not clear that building a dam is going, there are two possible, One is really people will have to move. So that we can measure the number of people we will be affected by that, correct? Or, another thing we are looking at is destruction of farmland, because that's also happening. But, there are many more criteria that we actually have not, we don't have the data for those criteria, but like even economic criteria, we have emphasized more, ecology and, social impacts, but populations, it may be that the population will benefit for every, energy nearby. So, yeah, it's not clear exactly how to measure this effect. But the big lesson, the big conclusion, again, we don't suggest build this dam or not. We actually have all kinds of metrics then to try to have a bit of a sense of how we would rank dams. So if a dam barely appears on the Pareto frontier, that is a good indication this dam is probably not good, correct? Because it's always dominated by others. Of course, our big message was, you need to really reason across many criteria, because if you just do with respect to connectivity, you have a solution. If you now add more criteria, you will have fundamentally different solutions. And more important, and another message we wanted to put across is, you'd better do this at a large scale, because if you just plan for Brazil, you are going to, basically kill all the connectivity and the sediment production, etc., for other countries. So that was kind of a big message in the paper. Really, you need to plan at the scale of the entire Amazon, the scale of as many criteria, or at least key relevant criteria, because otherwise there will be substantially foregone environmental and economic benefits.
So thanks for a fascinating talk. It was just I was just curious about one specific thing, which is when you're doing the eBirds, the bi-level optimization thing. How do you so I understand the problem, right? That is that you don't know, that you want to incentivize people to go to places where they wouldn't ordinarily go. But how do you estimate their utility functions to begin with to design the reward structure?
Yeah. That's a problem that you learn over time, correct? But, so initially you have some sense and you assume, part of maybe hypothesize distance is an issue, etc. But over time you get these data, correct? And your problem is really, and that's a beautiful question, because your problem is exactly, one problem is what I call the pricing problem, is how do I place the points, assuming I know how the borders are moving, and the other one is learning the presence of the borders, the e-borders, for us to predict their movements. And, that's a learning problem. And if you, a little more technically, and actually this was, beautiful work by Ye Shang, this is, the pricing problem is, how to set up the points. And we actually formulated the identification problem as almost a knapsack problem, where the borders, the e-borders, are trying to collect as many points as they can, but we have to learn the coefficients of the knapsack. And, interestingly, because the knapsack actually can be solved again with dynamic programming, then dynamic programming can be flatten and transform into inequalities, we actually are able to fold the problem of the users into the main one as a single one, and again we can provide some approximation results. But indeed, part of the issue is to learn the preferences, and that is what we do over time. Very good question.
Dave.
Yeah, thank you. It was really fascinating and great. It's just great to see this work for the world.
Yeah, thank you.
I have a question about the dams. I was wondering if over time dam technology will get better and maybe cause less each dam may cause less damage. The whole Pareto frontier might get better. You'll have better choices in the future, I guess. So could that play into your thinking, what to do now? If you know, if it's true that in the future the Pareto frontier will be better, you might think about what to do now, knowing later on you'll have better things.
Yeah, I guess, maybe part of that is even the technology is changing. For example, now you are actually seeing, and we are looking into actually a broader notion of portfolios as opposed to just dam portfolio. Now we think of, in fact, we are working with Colombia, this Magdalena for a net zero agenda, and there we are thinking not just dams but other renewable energy. And dams, for example, are playing a key role in terms of using the dams to actually also store energy. That's becoming a big thing. There are other crazy ideas. In fact, we have a little piece in Nature which I honestly think it is a bad idea, and we kind of say it's probably a bad idea, but now a lot of countries are using, the area of the dams for floating photovoltaics, which, it's another way of harvesting solar energy. But I think that's going to kill all the, everything, because they then are deprived of sun, so that sounds to me. But, so we are going towards, this idea of different portfolios with different types of energy in addition to hydropower, wind and solar, etc. And I think, that may make more sense to understand the energy needs of countries. So. Very good question. But hopefully, this reminds me, I thought your question was very good, and maybe I'm going to answer in a very different way. But for example, I just mentioned we just started and we got this AI Institute, NSF AI Institute, and there, a big thing is carbon markets. And we think that, the Pareto frontier is, and so that's, typically the Pareto frontier doesn't move, that's how it is. But, if you find new opportunities for, like you start using carbon as a commodity, actually now the Pareto frontier can move forward because now there are opportunities, you value carbon. And in fact there, for example, I think, you guys know about food stamps, where you have all kinds of, sugary stuff, and because there's all this lobby for corn syrup and all this thing, and in fact it's actually very hard to have like the other kind of healthy meals because of the, all the lobbying, etc. Because it's anyway. But I think, for example, if the farmers can start playing in this carbon market, then maybe they will be less interested in producing all the other. They now focus on, the carbon and value the carbon. So we think that the Pareto frontier actually can move forward because of that. So that really is when there's fundamental, different technology or different way of valuing the commodities. So very good question. Yeah.
I have a couple of questions. It's always about the DIMACS. Now, first of all, does the impact of the DIMACS, is it independent or it is combinatorial?
Very good question. Yeah. I mean, it is, if they are very close to each other, they definitely affect each other, correct? But typically, because of that, they are, quite far from each other. So we don't assume they are affecting each other. But we do, compute the cumulative effects, but we consider them independent. Good catch.
Okay, so are the criteria independent? So is it preferential independence about the criteria? Because if we build the Pareto frontier with the idea that they are independent, it will take a certain shape. But if they are not, so if preferences on connectivity are related to preferences on some other...
On fish, and they are, yeah, but...
Then in this case, the Pareto frontier will be quite different.
Well, but because we compute them simultaneously, they affect each other, so that is accounted for. What I think is interesting and what we are looking into is to what extent we can identify key criteria that will somehow encapsulate a set of criteria, because we cannot compute the Pareto frontier for a billion criteria, correct? Like for example, for the biodiversity, there are like 300 fish species. We are now thinking maybe let's try to even look at the phylogenetic trees to identify, key representative species, to compute the Pareto frontier for those species. But because we actually are, the fact they are dependent is not a problem, because we are computing jointly. I mean, one issue is, trying to estimate these species, because in the end we are going to try to compute how this will affect the abundance of the species. That, for example, that's why we also need, I was trying to give you a picture that all these things are somehow connected, like we really need very good models to predict biodiversity for us then to compute how these things are affected. So, yeah, very good question. But the way we are thinking is trying to identify key, more representative species, so then we don't have to compute the Pareto frontier for a billion things, because we can't, correct?
Now, my last question, not related to the dams.
Yeah.
When we were talking about, let's say, in which direction go in discovering new materials, etc., etc. No? Now, with we were confronted with a similar topic, which is the following one. You are constructing points of the Pareto frontier which are interesting because of their utility. But you want also to consider points of the Pareto frontier who might not be that promising, but they are very different. No? We have seen that in drugs studies. No? You want to develop new drugs, so for diseases, so you want to develop, there is a part of molecules that are promising, no? So you want to test these ones, not all of them, of course, but you also want to test some very different molecules. Although they are not as promising as the first ones, but because they are very different, they might be of interest because they could develop a completely new way. So it's not only how promising is the Pareto frontier, frontier, but also how diverse is the Pareto frontier. No? Do you see a way to how to do how to consider these two ways of let's say studying the Pareto frontier? No? Because the Pareto frontier is sometimes immense, as you have already said. No? So you want to focus in regions of the Pareto frontier, no? And then it could be interesting to keep part of the Pareto frontier. One, because it promises good results. The other one, because it is very diverse.
Yeah, so that's a very good question. And I guess, that's like a general question for us to study, trade-offs like in computer science, where you have these algorithms that, there's the exploration and exploitation trade-off, correct? And where you want, or if you go to the casino, you think this arm is the good one, you keep pushing it, but maybe you also want to, try the other ones, because who knows, maybe they will give you, a better reward somehow. So yeah, these trade-offs, for the Pareto frontier, we actually, exhaustively search the Pareto frontier. The results that I give you are exhausting going over the Pareto frontier. We can do this here a bit because of this unique situation where we have this river, so we can use dynamic programming, but in fact at some point, it becomes prohibitive, and the number of solutions is, crazy. I mean, it is really, billions, trillions, and so because of that, we are thinking what we are trying to understand is how can we summarize this Pareto frontier to policymakers, so that's one thing. But, another aspect that we are talking about, I think, is, really how to search spaces. And for, SAR, I mentioned this system here, which is interesting because this system, we are looking at what is called metastable materials. So metastable materials are materials that don't reach the equilibrium, so they can change. But, by looking at these materials, you can expand dramatically the periodic table. And I will give you a good example of a metastable material that's changing over time, but I guess most people don't worry about it, or diamonds. Diamonds is a form of carbon that is metastable. And of course, it's not changing, or it may take, billions of years to change. But because of that, you see, we are looking exactly at, in fact, this apparatus here is, really exploring different ways of synthesizing the material. So here you have that laser spike annealing is doing the annealing of the materials, and there we change the temperature and the duration of, basically you are zapping the material for, a second or so. But depending on how you do this, you can have fundamentally different materials, and so we are exploring exactly, that's what we are doing here. We are trying to uncover the entire, a bit of sample, and producing the different, this map of what you can do as you vary the temperature and the laser spike annealing. This is actually a case where you have a single composition, this bismuth oxide, but then we want to explore the entire map as a function of the temperature and the dwell time, because you can get fundamentally different materials. So we are building these maps to try to do that. So exploring, maybe a lot of the regions are not very exciting, but basically we are trying to characterize the entire regions and have what it's called the phase diagram, where you know that as a function of temperature and dwell time, you are going to get different materials. So I'm not sure if I answered your question, but essentially, you know, I think this is really this exploration business that, you know, it's very common for us to do in other disciplines. And it's about scientific discovery, you know, a bit like that. We are trying to automate this, you know, this process.
I think we're half an hour late.
We are half an hour late.
But he has a question.
Because you have that.
Okay.
So I'm afraid that the superior controller tells that we are
No, sorry for being.
but it has been a lovely discussion.
Thank you, very kind. It was fun. And I'm so happy that, you know, I put the Pareto here because I saw you guys, I said I need to talk about it. I didn't know what to talk, I mean, I could have talked about, you know, all these projects that I have here, and I picked 3 of these, so thank you so much.